So this will be the last part of organic chemistry that we'll be dealing with. Yep. So now now we're just like finishing off some little parts on the side, which isn't like it won't be too big and it won't be too hard, especially if you've done biology or if you know any biology and how enzymes work. This should be very straightforward, at least the end part should be. But the first thing we're finishing off is going to be chromatography. So I want you guys to understand from here. Where's my cursor? Where's my cursor? I want you guys to. Who does not want to do this? What do you mean? Where's the pen? The main thing I need you guys to understand is the mobile phase. Yeah, from here. So the mobile phase allows a object to move through the chromatogram. How many of you guys have actually done chromatography? Can you put your thumbs up if you've done chromatography? Because I know some places do. Okay. Okay. Because the main thing I need you guys to remember is the mobile phase. You don't really need to know any of this, like any of the rest of this stuff. By definition, maybe the definition of interpolate, but besides that, I can't think of anything else you'd need. And then over here, we'd have, well, the mobile phase, as I said before, and the stationary phase. And that's the other thing you want to think of. Other definitions that we'll cover as we do this. So the big thing that you need to the thing that you need to remember for chromatography is that chromatography is a separation technique. Yeah. So like steam distillation, fractional distillation, it's a separation technique. It allows us to separate compounds based on their chemical properties. No, well, here at water. Here it allows us to base them to move them based on those properties of how much they adhere to the stationary phase and how much they adhere to the mobile phase. And I'll explain what that means more in a second. The other thing that we can do with chromatography is that it helps us determine concentrations, yeah? And can also help us determine the presence of something. So the presence of a specific compound. We'll discuss that as well. So I've already discussed this part. And here we'll have a look at it. So here's paper chromatography, yeah? And essentially what we're doing here is this is the beginning of the experiment. We have our sample of origin, and here it spreads out into the multiple colors. And here is our solvent run, yeah? So essentially what's happening here, and we need and I'll remember that the solvent is water, yeah? And water is a polar solvent. Let's just remember that. So what does all of this mean? Essentially, yeah, what's happening here is that at the origin point, it's made up of a bunch of different components and compounds, yeah? Those things will move up the page depending on how much they adhere to the mobile phase. Now, what does the mobile phase mean? It's essentially how how connected to the solvent they are. Yeah, so how or like how strong their connection to the solvent is. So here the connection, so how they create that strong connection is that they're either the polar or they're non-polar. So here the one that adheres most to the mobile phase, the one that moves the highest is going to be red. And that implies that red is a highly polar molecule. Yeah? Because that adheres or it attaches to the solvent more readily. Yeah? than everything else. That doesn't mean it doesn't go into the stationary phase. The stationary phase is essentially the opposite. So here we have a non-polar solution. We have a polar solution, which means we have a non-polar stationary phase. Yeah. Here it will go into this. It will go into the stationary phase every now and again, right? But it won't go to it will revert back to the mobile phase very quickly. So you can think about it as if something adheres more to the mobile phase, it will it will be it's more likely to dissolve in the solvent than into the to what makes up the stationary phase. Yeah? Right, it will still go into the thing that makes up the stationary phase, but it will also go out. Yeah? So the stationary phase is the not moving, the mobile phase is the moving. The more it adheres to the mobile phase, the further it moves. So let's just say the blue dot down here, is the least polar, yeah? And it's probably the most non-polar. I'm making an assumption here. We can't be completely sure, right? But we know this one's the least polar because it adheres the most to the stationary phase, yeah? It moved the least, so it adheres the most to the stationary phase compared to everything else. So does that make sense for everyone? Does anyone have any questions? Okay. The big thing that changed. So here we've looked at paper chromatography, which is how far it moves up, right? Later we'll have high performance liquid chromatography, and that bases it that high performance liquid chromatography. And that bases it based on the time it takes for it to flow. Yeah? So imagine, right, if we had this part here, let's just say we had red and blue again, and we had a polar solvent, yeah? Red would move through the high performance liquid chromatography faster than blue would, yeah? The reason it would move through faster is because it adheres more to the stationary phase. So you can think about it as for high liquid chromatography, we're like basically just putting it into a tube and seeing how fast it goes through this tube. And here inside the tube it has let's just say it's a polar solvent, yeah? So if the solvent's polar, right, the mobile phase is polar, red will adhere more likely to that polar mobile phase and it will move through faster, right, and will get out the other side compared to, let's just say, blue, which will go in and it will go through very slowly. It will still go out the other end, yeah, but it won't do it as quickly as red will. So, does that make sense for everyone? Any questions about that? Okay. Okay. So here, in chromatography, a sample absorbs to the mobile phase once and dissolves into the stationary phase only once. Dissolves into the mobile phase only once and absorbs into the stationary phase only once. Are continuously absorbed into the mobile and absorbing the stationary phase. And are continuously dissolving into the mobile phase and absorbing to the stationary phase. So what do you guys think? A, B, C, or D? What do you guys think? So remember what I said. C. Yeah. Okay. So it isn't these two, right? Again, as I said before, it continuously, right, goes from mobile to the stationary to the mobile to the stationary to the mobile to the stationary phase. Yeah? So it has to be between C and D. Yeah? Now the answer is D. It's dissolving into that mobile phase. Yeah? You can think about it as it's like it's a solvent. It dissolves in a solvent. Yeah? And it absorbs to the stationary phase. So here the answer is actually D for this one. Yeah? It's a solvent. It dissolves in a solvent. This is a very wordy one. I don't think they'd make this big of a wordy difference between the two. But does that make sense for everyone? Is that all good? It's because it's a solvent. It dissolves in a solvent. Yeah? I think it's a bit of a more just like a picky, wordy sort of situation. So, here, the thin layer chromatography shows a polar stationary phase. It was developed using a hexane as the solvent. Which sample is the most polar? What do you guys think? Which sample is the most polar? Anyone else? So, here I think I know what you guys have done. Uh, so it's a hexane. Yeah, hexane is a non-polar solvent. Yeah. So that means the stationary phase is non-polar, which means the thing that moves the highest through it is actually a non-polar molecule. B is actually extremely non-polar, yeah? It has to be A, yeah? Because A adheres most to this polar stationary phase, yeah? It adheres to that stationary phase, which means it moves the least. So the answer has to be A here. Does that make sense for everyone? Okay. I'll keep moving forward. What about you, Meth and Blessing? What do you guys think? What do you guys? Okay. So here, this is just sort of this diagram here is meant to sort of represent. Well, here the concentration can actually be determined by the area under the curve. Yeah. Let's just say, this is a 1 molar solution. Yeah. And this area is like, let's just say, 500 like absorbance, or like, you know, we'll just say 500 absorbance, yeah, under the curve. And then we have this one over here, and this one was like, let's just say 750. That means this solution has a 1.5 absorbance. So it's basically saying, if you look at the area under the curve, they'll tell you what the area under the curve is. You won't have to do calculus to figure this out. Yeah, you can essentially find out. You can essentially find out what is going to be what the concentration of the solution you're looking at is. The other thing you can tell is you can tell the presence of something. So we know this is compound A, and if, let's just say, we're running another experiment, and our let's just say we were running another experiment, and we saw, like, there's all this stuff, and there's like, whoa, this one over here, yeah, right. This suggests the presence of compound A in this other solution. Let's just say it was like a petrol solution. Yeah, we just saw compound A in there. So essentially, right, if it has the same retention time, we will be able to find an chromograph. Yeah? So does that make sense? Those are the two other things we can do. We can determine what it adheres to, if it's more polar or less polar. Yeah? We can also figure out the area under the curve to find the concentration. Or what we can do is we can find, if we can find the presence of that thing. So does that make sense to everyone? Is that all good? Okay, okay. Thumbs up all around. Uh, The only thing that the the only thing that affects it is that if we're doing this sort of analysis, yeah, where we're like analyzing the area under the curve, we need to use the same HP we need to use the same HPLC with the same condition. So it needs to have the same length. Yeah, the tube needs to be the same length. We need to use the same solvent. We need to have it at the same temperature. Yeah, because all of those things will affect how quickly it will pass through. So if we have it at another, like for example, these aren't set values. Yeah, if I put B through another HPLC, I might get something like this. Yeah, and it's because the other HPLC has different conditions to it. Yeah. It has different laboratory conditions that it's running to. So I want you guys to be mindful of that. Yeah? Any questions? Is that all good? Okay. So it needs to be, the other thing is that we require it to be at the same conditions. Yeah? So here, these are some of the things that can affect the retention time. Yeah. So here, we usually talk about this in terms of high performance liquid chromatography. Yeah, essentially it's just that big tube and we're running the thing through that big tube. So it goes through. I know the machine looks something like this where it's got a bunch of swirls and shit in it, but it really doesn't matter. Yeah. Like this long tube can be represented like this. That's the whole idea. But these are some ways that changing the conditions can affect the retention time. Essentially, we don't want to change the conditions if we want to do analysis. If we change the conditions, then it's going to ruin our whole experiment. So, from here, have all of you guys seen a calibration curve before? Have all of you guys seen a calibration curve? It should be somewhat familiar to you from Unit 1. From Unit 1 and 2. Just thumbs up, thumbs down. What do you guys think? Have you guys seen this? Yeah, Salam. I would have expected you guys to. I would have expected you guys to see it. No one else to see it? Joe's seen it. What about Mia, Blessing, Sway, Am? Have you guys seen calibration curve before? No, you haven't seen calibration curve. So essentially, what we do is they essentially create a bunch of standard. They basically create a bunch of standard solutions. So solutions we know the concentration of. And here we find the peak area. Yeah. We find the peak area of these ones, and we plot them on a graph, and we create a curve. Yeah. So now we have peak area against concentration. So let's just say we have a concentration of 0.45. Yeah. A peak area 0.45. And then we go down, we can see that this is going to have a concentration of about 4.5 milligrams per liter. Yeah. So essentially, right, it allows us to find out well what the concentration might be in different what's it called? The concentration might be depending on what that peak area is. Yeah. Now the big thing that you need to realize is that we can only find peak areas inside our data, right? Does everyone here remember the phrase interpolating and extrapolating? Remember interpolating and extrapolating? Is that no? Yes, yes. Of course you know what it is in math, but it's like half of your fucking subject. Um, but if we go over here, yeah, if we extend this line out past the data set, we call this extrapolating, yeah? And extrapolating is unreliable, yeah? The reason extrapolating is unreliable is because we're assuming the trend continues outside the data set. But we have no idea if this trend goes like this. Or if it goes like this, you know, like logically it would go in a linear line, right? But it could go in some other direction, yeah? When we do interpolating, we use values within our data set. So here, 0.25 peak is within our data set because our data set is between 0.06 and 0.51. So does that make sense? Does that idea of extrapolating, interpolating make sense? You'll probably have to use interpolating more in fuels chemistry than anything else. Yep, what's up, EMF?
When we're told to like draw like a line through the values, like a calibration curve, do we do line of best fits or connect the bottom point and the top point?
We draw a line of best fit. So
Okay.
we draw a line of best fit, and we only draw that line in between the data set. If you want to draw it outside, you can do data. You can put dotted lines on because that represents we're extrapolating.
Yeah. Okay.
Yeah, but using his further maths brain. So proud of this guy. I love you, math. I love you. Anyway, consider the following changes that would be applied to operating parameters for a high-performance liquid chromatography setup with a polar stationary phase and a non-polar mobile phase. So decreasing the viscosity of the mobile phase, using a more tightly packed stationary phase, using a mobile phase that is more polar than the stationary phase. Which one of the following changes would be most likely to reduce the retention time of ethanol? So ethanol, is it A, B, C, or D? What do you guys think? A, B, C, or D? So mostly thinking about, is it polar, is it non-polar? I got a couple people saying B. Anyone else? Any other suggestions? A. Okay. I think some of you have got the definition of viscosity. Viscosity is the resistance to flow. So if we decrease the viscosity, we decrease the resistance to flow, which means we increase the amount. Wait, not my bad, gang, my bad, gang, my bad, gang, my bad, gang, my bad, gang. Are you right? That's fine. That's fine. The second one's fine because if it's more polar, right, it will the ethanol will be more attracted to the is it your bad, bro? Yeah, it is my bad, gang. So it says it using a mobile phase is more polar than the stationary phase. If the mobile phase is more polar than the stationary phase, that means ethanol, a polar molecule, would adhere more to that mobile phase. So I and all right. And here, if we use a more tightly packed one, Swayam, I'll ask you, why would that not reduce the retention time? Any ideas? Any guesses?
Like, can you hear me?
Yep, I can hear.
Is it because it has a greater surface area?
Yeah. So yeah, you can think about it as a greater surface area. The idea is that it can create stronger bonds. Yeah. So here, because we already know the stationary phase is polar, that means ethanol is already going to be attracted to that stationary phase. So if we make those bonds stronger by tightly packing them, yeah, then ethanol is actually going to be more adhere more to the stationary phase, right, and take longer to come out. So yeah, the answer is B. Does that make sense for everyone? Is that all good? Thumbs up, thumbs down, thumbs to the side, thumbs all around. Here, which one of the following changes is most likely to change uh, in fast elutions, lower retention times of a compound in an HPLC? So which one is most likely to result in a lower retention time? You might need to know these words. Just had to check. Yeah, I think he made it. Okay. Which one of the following is most likely to result in a lot of attention time? Here you might need to know the words mostly. You might need to know these sorts of words because they're like trolls about them. That like they'll enjoy using them for no reason. Like it's like telling a dog to do a flip. They'll do it. Like, have you ever seen a dog not do a flip before? So what do you guys? What did you guys get? We get A. Unk might have lost it. No, sometimes I just throw in those sorts of words, and you don't really need to know them because they're just like describing other things. But like, if they're gonna use them, you have to know them for the exam. Yeah. Anyone else got any answers? Because if we have Emeth, let Unk share his wisdom. I'm just gonna be known as Unk forever. I'm not that old, guys. Bruh. Okay, yeah. The answer here is A. Oh wait. Lower retention time, so decreasing the temperature. So increasing the temperature definitely won't increase the retention time. And if we... Oh wait, no. I'm dumb. Sorry. A would increase the retention time, so A is actually wrong. Yeah. If we decrease the temperature, right, it's gonna be more more viscous. Yeah. So decreasing the temperature makes it more viscous. Do you guys remember that from organic? Right? I covered it in the organic slides. Here, increasing the tube length will also increase the retention time. Yeah. Decreasing the size of the stationary phase. If we decrease the size of the molecule, they have a higher surface area, which means they have stronger bonds. So that's also going to cause stronger bonds, means we're going to have a higher retention time. So C is the only one that makes sense here. Yeah. We increase the temperature. Does that make sense? Is that all good? Any questions? Any comments? Any concerns? No, I'm just gonna get aired out. Thumbs up, thumbs down, thumbs inside, thumbs all around. Okay. But wouldn't increasing the temperature increase retention rate of reaction? No, we're not talking about rate of reaction here. There's no reaction going on. It's chromatography. We're not talking about rate of reaction. So it says here, when comparing experimentally obtained retention times to known retention times, which one of the following conditions must be identical? What conditions must be identical for comparing? But why would the same principle not apply? Because there's no reaction going on. There's no reaction going on here. There's nothing reacting. That's why. Like it's we're just putting a sample through. The sample isn't reacting. So you're right. It might react, but it's not reacting. Yeah. We have one person saying D. Anyone else? Anyone else got any ideas? Anyone? Piss me. You got some people saying C. Anyone else gonna guess a D? D. Okay. D. So here, the answer is D. Everything needs to be the same. Nothing can be different. Everything needs to be the same in order to compare the retention times. If there's anything different, then it will be invalid to compare the retention times. Does that make sense, Swayam? Because all of these things will affect the retention time. So temperature inside the column will affect the retention time. Pressure inside the column will affect the retention time. Type of mobile phase will also affect the retention time. So all those things will affect the retention time. Does that make sense? Anyone any questions? I can. Thumbs up, thumbs down, thumbs aside. Most of you guys got this one right, which is really good. So it's either that or you guys are all sheep, which kind of suck. So here, a mixture containing four primary alcohols was separated using high-performance liquid chromatography with a non-polar stationary phase and a polar mobile phase. Each alcohol contains only one hydroxyl group. The following chromatogram is shown. Which, according to the chromatogram, alcohol 1 has the highest retention time. Alcohol 2 would elute from the column first. Alcohol 3 is closest in polarity to the stationary phase. Alcohol 4 has the highest molar mass. So what do you guys think it is? So A, B, C, or D? And think like logically. What did immaculately reading and analyzing the question is to get me. Okay, man, just give me an answer, bro. There's one answer. So sometimes chemistry, you like remove answer options. Sometimes you can just find the correct answer option. It's a nice subject like that. Elude means leave, basically. Just means leave. So alcohol 2 will leave from the column first. Is that true? B. Anyone else? D. Okay. So, it's definitely not A because A has the lowest retention time, not the highest. It's not B, right? B isn't what leaves first. Number 1 is what leaves first. Yeah. C, right? If this was true, if C is the closest polarity to the stationary phase, it would have moved the less. It would have the lowest retention time. Yeah, but it doesn't. And here, that means D is going to be the answer, right? The reason why a higher molar mass means that it's going to be more adhered to the stationary phase is because it has a higher polar region, yeah? So think about it. If we compare like an alcohol like propanol, yeah? So this is propanol over here, to something like this, which is going to be, let's just say, 1, 2, 3, 4, 5, 6, 7, 8. So compare that to like a octane with a hydroxyl group on it. Yeah, the octane has a higher polar region. I mean non-polar region, which means it adheres more closely to the stationary phase. Is that all good? Any questions about that? Any comments? Any concerns? Okay, chill. So here a particular HPLC instrument was used to separate mixtures of two chemicals. Each separation was done under similar conditions. The mobile phase used was either water or hexane, and the stationary fuse was used for each, and the same stationary phase was used for each separation. For the mobile phase given the first in the first column, which one of the following gives the two chemicals expected to have the largest difference in retention time? So which one of these two would create the largest difference in retention time? What do you guys think? Not presuming longer the molecule, it has a longer retention time. Yeah. That one isn't. It's not necessarily correct that if it has a longer, if it's a longer molecule, it's a longer retention time. But I'll let you guys do this one. What do you guys think? What do you guys think? Which one of these would lead to the most separation? Lead to the largest difference in retention? Anyone have any ideas? Is it A? Is it B? Is it C? Is it D? Is it Lamau? B perchance, okay. What else? Anyone else got any ideas? Unk, go get like coffee, you look tired as fuck. I went to bed at like a reasonable time as well. Someone's saying B. I don't drink coffee as well. I drink pure, unfiltered. I drink food. Tastes good. I'm fine though. I'm chill. I don't drink energy drinks either, bro. I don't have any of that. I don't have any of that stuff. Uh, I got two people saying B. I didn't get anything else though. So here, the answer is actually not sure, but can be A. It's A. Yeah. The reason being is because hexane is a non-polar molecule. Yeah. So that means here the polar molecule and the non-polar molecule will probably have the largest difference in retention time than if it was in water and they had two polar molecules. It's basically like you want the two molecules to be a different polarity, yeah? So these two are the same polarity and these two are the same polarity. So you'd expect them all to have similar like one would still have like a lower retention time than the other, but this one would cause the greatest difference here, yeah, because they are literally different polarities, and here the hexane creates the biggest difference here, yeah, because here, right, the butane will move through really faster, but the butanoic acid won't. So does that make sense for everyone? Does anyone have any questions about that? Is that all good? Okay. So here we'll just look at like I just put these last few slides in here because because I don't think I focused on this enough. With organic analysis, we're using these techniques in combination with one another. We're not using them by themselves. We're using them in combination with each other. So I want you guys to have a go at this question. So using this IR and NMR spectrum, what answer is it? Is it A, B, C, or is it D? What do you guys think? What do you guys think? Honest to God, on God for real. And then we'll talk about the fun stuff, which is going to be the chiral sentence. Yippee! Have you guys ever enjoyed looking at chiral centers? A, because it's the longest. Okay. Remember, you need your best friend to do this. Don't try and use your eyes and do this. Use your best friend. He knows everything. Like literally, he literally knows literally everything about literally all of chemistry. Right? Does no one got any ideas? We have one person saying C. Okay, anyone else? Any other answers? D. Okay, we've Salam saying D. Anyone else? C. Okay. So this one here. This one here has three environments. Right, that's what we can see. And this one over here, we can see this group here. There's nothing over here, which means that it can't be this OH and it can't be this COOH, right? We'd expect a peak over here somewhere if we were going to get those. Yeah? Who is trying to join? Oh, Daniel. What's up, Daniel? Never mind. One right, one wrong. So it can't be those two because we don't have this peak over here. And we can see that it has the C double bond O peak. Yeah? Bro, what the okay. Anyway. So we have the C double bond O peak. So that means it has to be one of these two. How do we just choose between these two? Well, here we have three environments that we have. Yeah? This one down here, if we draw this molecule, yeah, it's gonna look something like this. Because of the symmetry, right? These two carbons actually share the same environment. And then this carbon in the middle has a different environment from those two. So here, there's only two carbon environments here. So that means D is not the answer, and C has to be the answer here. Does that make sense for everyone? Is that all good? I was right. Okay. Says that after changing his freaking answer, bro. Holy shit. Daniel, we're doing some of the stuff that we did yesterday, so if it doesn't make sense, just watch back through the recording. So here, a research uses a combination of spectroscopy techniques to determine the structure of a molecule. Which combination of spectroscopy techniques provides the most information about the molecule's functional group and number of carbon environments? Which one of these would provide the most? So you got BB, got BB, AB, PP, AP, pop, 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 pop. So yeah, we have here answer option B is the answer. Yeah. A isn't because the mass spectrum only tells us about the molar mass, right? It won't tell us and potential fragments. It won't tell us about the functional group. The C NMR does, yeah. And here that C has the same problem, and so does, and D has absolutely nothing to relate to either of those two things. So here, which instrumental technique is most suitable for determining the functional group present in organic compound? Is it A, B, C, or is it D? There's one person saying C. So yeah, the answer here is C. Again, mass spectrum doesn't tell you anything besides the molar mass. So we use the mass spectrum here because it tells you more information than, oh shit, okay, I just skipped through a bunch of stuff. Okay. Yeah, because the mass spectrum tells you a whole lot more. So does that make sense for everyone? Does anyone have any questions about that? Is that all good? Thumbs up, thumbs down, thumbs to the side, thumbs all around. This one. So now we're looking into the medicinal chemistry stuff, right? All I have are questions, but watch the videos. Okay. So I think the only thing that is really new here is maybe this idea of race mates, that there's two different types of a chiral compound, two optical isomers, it's 50-50. And it's also this idea of an optical isomer. An optical isomer is two non-superimposable mirror images of the same compound, right? Which bend light in different ways, yeah? Because they have a different 3D spatial arrangement, yeah? So optical isomers are two non-superimposable mirror images of one another that bend light in different ways, right? They bend light in different ways because they have different 3D spatial arrangements, yeah? And we're going to talk about that 3D spatial arrangements in enzymes when we get to them. I know, Swayham, I can feel you just like buzzing with joy. You're like, ah, yes, year 12 biology, it's finally useful. I know, it brings a tear to my soul as well. I love bio. Alright. Oh yeah, shit, I forgot Daniel, you do bio as well. So, before we start on that, we have solvent extraction, yeah? Finally a use for that paper. Okay, so here we have the solvent extraction, yeah? Essentially, what we're doing here is we're trying to separate, yeah? We're trying to separate everything. So here, right, what we want is we want the nonpolar molecule, yeah? And we're using the same idea from chromatography, yeah? So here we have the nonpolar solvent. So we have here a bunch of, in this nonpolar solvent, we have a bunch of polar molecules and nonpolar molecules. And we want to remove these nonpolar impurities. So what we're going to do is over here, we're going to fill it up with water, yeah? And the water is going to dissolve the polar molecules because like dissolves like, yeah? So we'll dissolve all of these polar molecules. Maybe some of the polar molecules might stay in the solution, right? Some of the non-polar molecules might go into the water, right? It's not a perfect technique, yeah? But essentially, then what we do is we funnel it all in. And the majority of what's down here should be the desired non-polar molecule. Now, obviously, we'd repeat this process over and over again in order to get it as pure as possible. Because here, as we can see, that we're still going to have some polar impurities. So we're just going to keep doing that refining until we get only polar impurities, yeah? And here, we just want to remember, higher density stuff goes down, lower density stuff goes up. Think about like if you put an egg in water, right? Like egg in water usually goes down, but if there's a bunch of gas build up in it, it will go up. That's why you don't eat rotten eggs, because they're bad. So that's the idea of solvent extraction. Now, these are two molecules that we use solvent extraction for. Now, you do need to know the molecule. You need to be able to draw this whole thing out, yeah? So I'll ask Kavinu, how do you think you memorize that molecule? Alright, how many of you could tell I was joking? You don't need to draw this out. I promise. You don't need to draw this out, bro. I was just trolling. It'd be funny if you had to draw it out. But essentially the idea is that here, this is wait, did you ask me? No. Yeah, I low key. No. You don't have to draw either of these things out. Yeah. If you had to draw these out, they'd give them to you. Yeah. No, I called on Kibinu, but he didn't reply to me. I'm so sad. But essentially, the big thing that we see is that these are what some medicinal molecules or active ingredients look like. The active ingredient is basically the thing that we want to get out of it. Yeah. So here in tea tree oil, the active ingredient is this, and whenever we are trying to extract tea tree oil, we're trying to extract that active ingredient. That's the thing that we want. Cav low key quiet, I know, bro. So, like over here, this is the active ingredient in, I don't even know how to pronounce that name, but like it's the active ingredient of some medication here, yeah? So if we go forward here, right? A cosmetic brand is looking to use solvent extraction to extract the compound grandinol from roses. Would grandinol dissolve better in a more polar or non-polar solvent? What do you guys think? Do you think it would dissolve better in a polar or non-polar solvent? So one person says polar. One person says, another person says polar. Does anyone else say polar? We have another person saying polar. So here, I would argue this is a non-polar one, yeah? Because it has a, like here, there's only one polar region over here. It's going to be this part, yeah? And we're going to have this huge non-polar region, yeah? There's only this small polar region. So it's actually better us to use a non-polar solvent when doing solvent extraction. So here, solvent extraction is another separation technique, yeah? So right now we have 4 separation techniques. Simple distillation, fractional distillation, chromatography, and solvent extraction, yeah? So I'll keep moving on. Does that make sense for everyone? Is that all good? Any questions, any comments, any concerns? Give me the thumbs up, the thumbs down, thumbs side, thumbs all around. Thumbs down, what's up in there? What's wrong? Hit me with it. Hit me with it, bro. What's up? Unmute.
How do you know which is like a polar and non-polar?
Yeah,
feel like
no, it's,
that-
you make a good point, I think it's more or less just because of how big this polar chain is, yeah? That we can call it, polar. But I feel like in the exam, if you argued both sides, I'd give you the mark, yeah? Because technically your chemistry is correct.
How do you argue like both ways?
So, you can...
Like-
So here, you can argue that the presence of the hydroxyl group means that it produces those hydrogen bonds, which will mean that a non-polar solvent is more useful here. The other thing that you could argue is that because it has a very big non-polar region, yeah, then that might actually be better to use a non-polar solvent. So you could actually, I think you could argue both in the exam. However, I think because of I think because of, if you guys remember fatty acids, yeah, fatty acids are capable of producing hydrogen bonds. However, we don't think about fatty acids as polar bonds because they have very large non-polar regions. So I think the thing that you'd want to focus on there is how big is the non-polar region. They probably won't ask you something about this in the exam, yeah? But you want to think about how large of a polar region would be. They'll make it really apparent if it has a very large non-polar region. How's that sounding, man? Yeah? They'll make it...
Yeah, that's pretty good enough.
Yeah, they'll make it really apparent. They're not going to be like, yeah, here's this molecule right here. Right? Would it be better to use a polar or non-polar? And then they choose the answer as non-polar because apparently it having 2 carbons that are non-polar means that the polar region is like completely obscure, you know? Like that's complete bullshit. But move on from that. Now, this is the same simple distillation apparatus that we saw before. Again, it separates 2 compounds of very different melting and boiling points. It separates 2 compounds of very different boiling points. Yeah, that's what we want to remember. Now, if we go further, we want to go through this idea of steam distillation. Yeah, essentially, how steam distillation works is that for compounds that decompose, that are heat sensitive, right? Because if we heat them up, they'll just break down. We don't want that to happen, yeah? So we can't use regular distillation because getting the compound itself to boil is very hard. But essentially what we're doing is that in here we have water, yeah? And lots of our medicinal compounds are polar. So we use that fact and we know that they're going to bond to this water. So what we're going to do then is that we're going to heat up the water. And we're going to boil the water so we have our water molecule. And it will, like, while it's going up, it will take along with it a piece of our medicinal compound. We'll just call the M for medicinal, yeah? it will take this M for the medicinal compound. So here, it's not actually that the medicinal compound is being broken down or being boiled. It's that water is being boiled and that the medicinal compound is still connected. Yeah. Now we don't really think about it in that sort of way for gases, but that's how this works. Yeah. It's dragged along with it. Yeah. So the water is boiled and the medicinal compound is dragged along with it. So it comes back through here. The same process effectively happens. Yeah. And then we have our whole solution being separated down here. With water at the top and the other thing at the bottom. Does that make sense? So the main thing that you don't need to really remember the process of steam distillation. It's more you need to remember when we use steam distillation or why we might use steam distillation. It's to preserve this desired product. It's to prevent this decomposition, or it's to minimize the decomposition. Remember, minimize, yeah, and reduce the temperature required to vaporize it. So here, think about it. These medicinal compounds, they're very, very large, right? They're more likely to appear as solids. So it's gonna be very hard to it's gonna be really hard to boil them. Yeah. So that's another reason why. Anyway, does that make sense for everyone? Thumbs up, thumbs down, thumbs aside, thumbs all around. What do you guys think? So, okay, I'll keep moving forward then. And this basically you essentially the idea is that you repeat this process again to get it. Like if you repeat it again and again, it will distill it more and more and more until we basically have just a pure compound by itself. That's the whole idea of this representation. So I'll keep moving on. So here, an appropriate pair of solvents for use in solvent extraction is heptane and hexane, heptane and water, water and methanol and water and deionized water and seawater. What's going to be the best? The best, like no one ever was. To catch them is my real test. To train them is my heart. Pokemon. I will travel across the land, searching far and wide these Pokemon to understand the power that's inside. Pokemon, gotta catch it outside food. So what do you guys think would be the best thing for a polar effect? Ankh has officially lost the plot. Ah! Holy on God. What do you guys think? We got A. What is blood on about? But can you guys just pick the answer? On God, for real. Oh wait, it's different. So B, 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 B. Yeah, B is the correct answer here. Remember, we want them to be of different polarities. So it can't be A because they're the same. It can't be C because they're the same. It can't be D because they're also the same. Just because one is deionized water and one's seawater doesn't mean they have different polarities. Here, which one is the most appropriate technique to separate hexane and octane? What do you guys think? Solvent extraction, distillation, decomposition, isolation. What do you guys think is the most appropriate way? A. Anyone else? Anyone else agree? Anyone else disagree? Yeah, A. I can't reach for plastic. Yeah, I mean A is the correct answer here. So yeah. So A is the right answer. We have never heard of B and D. In fact, we're probably trying to avoid B and D. And C only works if there's a different what's it called? Only works if we have a what's the phrase again? Only works if they are different polarities. Here, why is steam distillation preferable to simple distillation for purifying oils? Oils have a higher boiling point. Oils are heat sensitive. Steam distillation prevents decomposition of oil. D. All of the above. What do you guys think? What do you guys think? A, B, C, or D? What do you guys think? Oh God. One person saying D, one person saying C. Anything else? Anyone else want to take some guesses or have some go? Beep, beep, beep. So here, the answer is D. Yeah. Steam distillation does all of these things. Remember those are the three things that I are highlighted about steam distillation. Those are the things you need to know. Is that why we would use steam distillation over the simple? Yeah. And why it's potentially better in some specific scenarios. So, okay. Here, okay. This is just showing off some large organic molecules. These are what we consider medicines. The big thing that you want to know about medicines is they're highly polar, they're very large compounds, and you should expect a lot of benzene rings. Like a lot of benzene rings. Like you'll see them basically everywhere. Like every single molecule that you'll look at is going to have some sort of benzene ring or aromatic ring. Aromatic ring, that's what we call them. So here, this one might not be a benzene, but it's definitely an aromatic ring. This one's just a hexane, yeah? If any of you guys know, if any of you guys know the structure of ATP, it looks something like this. It starts off like this, double bond, and double bond, this, double bond here, this. We have it in here, here. And then we have our oxygen. Here, we have our hydroxyl group. We have this one, which is a CH2. I think I'm missing a CH2 in between here. CH2, and this one is going to be O, P, O, P, O, P, O. This is a double bond O, this is a double bond O, this is a double bond O, and here we have O minus, and O minus. This is a minus as well. So that's what an ATP molecule looks like, and even this one has some form of benzene ring in it over here. Yeah, you don't need to know that. I'm just showing off that like these compounds are very big. Yeah, you should expect very large compounds. Now the big thing about this slide is essentially showing off that for us to be able to use this specific molecule, it needs to have a specific shape. Or for an enzyme, do we need to know how to draw and identify aromatic rings, benzene rings for this unit? You need to know what an aromatic ring and a benzene ring looks like. Yeah. Well, you need to know more about the benzene ring. Yeah. But you don't really need to know anything specific about them. You just need to be able to look at them and identify that's a benzene ring or that's a cyclohexene. Yeah? You just need to be able to identify them. You don't need to be able to do anything crazy with them. You just need to know, like, mainly just the structure. The big thing here is that, or the big thing that I want to focus on is that this is going into the idea of the active sites and the active sites of enzymes. They have to be, the active site has to be a specific way. It needs to be perfect for the enzyme to fit into it. Yeah? Nothing can be wrong about it. Loki scuffed, they never even talked about it. They don't talk about benzene at all. It's a bit like, they don't talk about benzene that much, but benzene and cyclomolecules, so that's the other aromatic ring that we deal with. There's other ones as well, but we don't look at them as much. Like we have like toluene and that sort of thing. But the main thing is you just need to know those. Just purposely setting me up to lose. Okay. The big thing that I want to stress out here is that it's just it has to be perfect. Yeah, everything has to be perfect about it. We can't have a single discrepancy here. So, yeah, these are the things that I said before. They're polar, they're relatively large molecules, and they contain rings. So if you guys want to look at it, there's no universal indicator, right? But this is what many of them contain. Obviously, we might have one that doesn't contain a ring or is not polar, but that's just to troll you at that point. So here, which one of the structures is most likely to be a medicinal molecule? Is it A, B, C, or D? This one here we call toluene. Find the element IMCQ. That's the most bizarre thing I've ever heard in my life, bro. Yeah, so we have a bunch of people saying D. Yes, it's D, right? You'd expect D because it's a large molecule, it's polar, and it's got a lot of rings. The other thing, like here, this is technically a ringed compound here, but this is a ringed pentane. So, oh, okay, yeah, no, have a go at this one. Which one of the following groups is likely to be present in thymol? Which one of these groups is most likely to be present in thymol? There is a right answer here. Just me. If any of you guys get into like medicine, you can drink the thymol in all the antiseptic wipes. Trust. Yeah, it's kind of tasty if you don't follow up. Trust. It's bitter. It's bitter. It's still alcohol, but it's like. Damn, I'm actually making it sound like I've drank this shit before. I haven't, I swear. Oh god. Anyway. The answer is C. B literally cannot be present in an organic compound, like literally. A, there's not like the peak over here that we'd normally see. And D can't be the compound because it'd have a much broader peak. It'd be like way broader. It'd be like this sort of length. It was D. Man is getting drunk on wipes, baby wipes. Okay. So, let's now go into this idea of chiral, yeah? We have chiral and achiral, yeah? Now, chiral compounds, we usually think of our hands, yeah? They are non-superimposable mirror images of one another, yeah? Your hands are mirror images of each other. So there's no way that I can turn this hand to look like this hand without doing a reflection, yeah? There's no translation I can do to make these two look the same, right? However, for an achiral compound is a superimposable mirror image. So essentially, if we have something and its reflection, it's basically perfectly symmetrical so that they can fit over each other perfectly. Yeah? So does that does that idea of chiral and achiral make sense? A chiral compound is a non-superimposable mirror image of itself, so they can't be overlaid by each other. But a achiral compound is a superimposable mirror image of each other. Yeah, so they can be overlaid over one another. Is that all good? Can I get thumbs up, thumbs down, thumbs to the side? Does that concept make sense? Okay. Okay. Anyone else? So here, right? This is what we mean by so like this is I won't explain why this is chiral yet, yeah? But this is a chiral compound because here, like the only way that I can get this compound to look like this compound is if I reflect it, yeah? There's no way I can reflect in the real world. So if I rotate it, if I translate it anyway, like have you guys ever seen those videos where it's like slide, rotate, translate, those sorts of things, yeah? I don't know. Maybe you guys grew up with different things, but like dude, I sound so old saying that. But essentially, the only way you can do this is to literally reflect it, and we can't reflect in the real world, yeah? Like we don't have mirrors everywhere. So what we have to do is we have to be able to rotate it. And essentially, what's happening here is that the 3D spatial arrangement is different between these two. The 3D spatial arrangement is different between these two, which makes them non-superimposable mirror images. Because here, it like this one, I can't rotate it in any way, yeah? In order to get it to look like this. I can't, yeah? And the 3D spatial arrangement, if I looked at this in 3D, right, there's no way for me to be able to like twist and turn it around. I wish I had like I wish I had, Evo has, like when the Clown students do it, Evo has a really nice model where he has the carbons in different places. He tries to twist it in a way that makes it look like a suit, like that tries to turn it into each other, but it won't. So the idea, guys, I think he's talking about the first Rubik's Cube ad, maybe. But essentially the idea is that we, like, this is what we mean by a chiral compound, yeah? So, here. Now, why have I shown you this slide? This slide basically shows absolutely nothing. But the idea is a chiral center, this A star, right? This is what we call a chiral center, yeah? A chiral center A star will be represented by having 4 different R groups. So if we look back over here, this one has 4 different environments surrounding it, yeah? That's why it is considered a non-superimposable mirror image. Because if we had 2 H's here, if we replace the fluorines for H's, yeah, there's a way that we could rotate them so they would look the same, yeah? There's some way we could rotate them so we can make them superimposable. So that's what we call the chiral center, is that they need to have 4 different environments surrounding them. See that I'm using the word environment and not atoms, yeah? It's 4 different environments, and it needs to be 4. It can't be 3, it can't be 2, it can't be 1. It needs to be 4 distinct environments. So here, right, I'm just going to ask you guys, do you think this compound is chiral or non-chiral? What do you guys think? Is it chiral or non-chiral? So we have one person saying non-chiral. Anyone else saying non-chiral, or is someone going to say it's chiral? What do you guys think? Non-chiral. 9. Chiral. So here, this one is a chiral center, yeah? Here, this C isn't a chiral center, because 3 of its environments are the same, so it's not a chiral center. But this carbon over here, it contains a chiral center right here, because it's surrounded by a bromine, a fluorine, and a hydrogen, yeah, by itself, as well as a carbon bonded to 3 fluorines, yeah? That makes it a chiral center because it's surrounded by 4 distinct environments. This part of the carbon is chiral. This one isn't chiral. So we call this one the chiral center. And we call this whole molecule chiral. Yeah? Does that make sense for everyone? Is that all good? Thumbs up, thumbs down, thumbs to the side, right? That's how we determine chiral. It needs to be surrounded by 4 different distinct environments. Yeah? Anyone else want to put there? What's the criteria for it to be chiral? It has a chiral center and it doesn't have a plane of symmetry. So we'll deal with that second part in a second, but it has to have a chiral center for it to be chiral. That's what it means for it to be chiral. It needs to have a chiral center. Yeah, just one. If it can have multiple, we can have a compound with 2 chiral centers, yeah? That's still chiral, but for it to be a chiral compound, it needs to have 1 chiral center. So, essentially, this just shows off that it's a non-superimposable mirror image of one another. Now, the phrase that we use for this is we call this an optical isomer, yeah? Or another phrase you might hear is N-N timer, yeah? They mean the exact same thing. So we have optical isomer, and the specific type is an NM timer. Now, there's multiple different types of optical isomers. I wouldn't go searching. So if there is 2 or 3 non-chiral, but one, it is just a chiral compound. Yes. So here we can use these 2 phrases. Now, don't search up optical isomers for if you want practice questions or understanding behind this. It will tell you about like trans and cis isomers, which they don't cover anymore in the study design, right? So here, right, we call this an NN timer or an optical isomer, yeah, of this compound, because it has a different 3D spatial arrangement. It bends light in a different way, yeah? Now, the only thing that I want to point out about this is that the number of NN timers this compound will have will be equal to N to the, 2 to the power of N, yeah? And what does 2 to the power of N mean? Essentially, N is the number of chiral centers this has. So because this has 1 chiral centers, there's going to be 2 different NN timers for this one. So there's 2 over here. If we had something with 4 chiral centers, it will have 16 different 3D spatial arrangements. Yeah. If it had 8 NN timers, if it had 8 chiral centers, we'd expect a whole bunch of spatial arrangements. And do you see how we're going to run into a little bit of problem? The more chiral, the more we have chiral carbons, right? We'll have different 3D spatial arrangements, which creates this big issue of, well, which 3D spatial arrangement actually works for a specific enzyme? That's going to be what we deal with in a bit. So here, right, ibuprofen is a chiral molecule used as an inflammatory to treat fevers. Which one of the atoms, 1, 2, or 3, is chiral? Now, multiple of them could be chiral, but which one of them do you guys think is chiral? Is it 1, 2, or 3? What do you guys think? So C, if it's surrounded by 4 distinct environments. You think 3 is chiral? Okay, 1, 1, 1, 1, 1, 1. I don't think he said it enough, guys. Chat, I don't think he said it. 1. Do you get any ibuprofen? So, we'll zoom into each one of these. So this one here, 1. It's C, O, double bond O, another C over here, yeah? This is only bonded to 3, it's not chiral, yeah? So 1 isn't chiral. We'll have a look at 2, yeah? 2 looks like this. So C, C, H, 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 C, O, double bond O, H, and this one over here is going to be bonded to a C, which is bonded like this to a C, and 1 down to a C, yeah? So do you just have Alzheimer's? So do you... Okay, So here, number 2, because it will have an extra hydrogen that we're not showing off here. Yeah? Number 2 is a chiral center. Yeah? This one is a chiral carbon. Okay, nice one, Daniel. And then 3 over here, right? 3 is the same problem as 1, right? This is what 3 could look like. It's only surrounded by 3 molecules. It's not a chiral center. So, the other thing that we have to point out is that does it have a plane of symmetry? If it has a plane of symmetry and it contains a chiral center, it is considered a chiral. If it doesn't have a plane of symmetry, it is just considered a chiral molecule with multiple chiral centers. Yeah? So a plane of symmetry means that it's a chiral. Yeah? So this slide is a very good determiner of... Put your hand up and ask. That doesn't make sense. What doesn't make sense?
Like how 3 is not the, what was it? Number 1 is not the chiral center, whereas 2 is, because like 2 is similar to the one that's below that, and so is 3.
No. But so one doesn't. One is like not bonded to 3 distinct groups. Yeah, it only has. Wait. It only has 2 bonds. Yeah, so 1 only has 2 bonds. Like only has the 3 bonds. Yeah, it needs to be bonded to 4 distinct groups. Remember. So here, this one's only bonded to an O, a double bond O, and a C. Yeah, there's only 3 bonds there. There's only 3 distinct groups. It needs to be 4 distinct groups. Does that make sense, Emeth? And the same thing with this one down here. Remember, this aromatic ring looks actually, well, this aromatic ring looks something like this.
Are you saying like, in terms of groups, are you saying like different elements?
Yeah, not like they're not different. They can be the same element. They just need to, like, remember when we talked about hydrogen and carbon environments yesterday? They need
yeah.
to.
So it's basically that.
Yeah. So here, this one also, right? This is carbon 3 over here. It's only bonded to this. It's only bonded to 3 groups. One over here, one over here, and one over here. Yeah? It's not bonded to 4 distinct groups. Does that make sense, Emeth?
Yeah.
Okay. So here, does the idea of an achiral carbon make sense? Does an achiral molecule make sense for you guys? Thumbs up for Salam. Anyone else? Okay. What about Kavinu, Blessing, Daniel? Daniel can't do reactions. Okay. So, 8. Now, why does the chiral center matter? Because of, as my biochemistry professor says, right? 2 of you know my goat, Nathan Habila. Basically, the 3D spatial arrangement matters. Yeah. If we don't have the correct 3D spatial arrangement, receptors in the body or enzymes won't be able to detect that compound because they are specific and complementary. Yeah, specific, right? Meaning that they're specific to the molecule, and complementary being like, okay, well, if this is going to be a rectangle, it needs to have a rectangle hole in it. Yeah. So it needs to have a rectangle hole in it, right? That's why this one doesn't work over here. Because this one is not specific and complementary. Yeah? It needs to be specific and complementary. Yeah, this is bio, bro. This is bio. Emeth, your favorite word. So here, right? These are 2 different optical isomers, right? We have the optical isomer R and S, yeah? These 2 have different 3D spatial arrangements, which means they interact with light in different ways. They reflect light in different ways to each other, yeah? But this also means that only one of these, if they were used in the body, could be used as a medicine, yeah? Because one of them won't fit into the receptor because it has the wrong 3D spatial arrangement. Well, one will fit in the receptor because it has the correct 3D spatial arrangement. Yeah? Does that make sense for you guys? Is that all good? Thumbs up, thumbs down, thumbs to the side. Yeah. Everyone doing bio is like, yippee! My knowledge is finally coming in useful. I'm not just analyzing DNA or something like that. So here, which one of the following atom or carbon atoms shown is a chiral center? Which one of these is a chiral center? Is it A? Is it B? Is it C? Or is it D? Abracadabra. Abracadabra. Talking about you, Swain. Yeah, so B is the chiral center here. Because B is bonded to 3 distinct groups. D is bonded to, 4 distinct groups. D doesn't have 4 distinct groups. C is only bonded to is only bonded to 3 distinct groups, and A is bonded to 2 hydrogens, which means it doesn't have 4 distinct groups. Kabinu woke up from his deep slumber, but that's what I'm saying. So yeah, it's D. Which one of the following molecules is chiral? Which one of these is chiral? Chiral center. Which one of these is a chiral center? Which one of these is chiral? Is it A, B, C, or D? Is it A, B, C, or D? Is it A, B, C, or D? What do you guys think? It is not A, because A is bonded to 3 groups only. Like both, this guy must think life. Okay, buddy. Okay. God forbid Bo is enjoying life. So 2 people saying D. Anyone else? C. Anyone else? Anything else? So the answer here is C. This here is a chiral center, right? This molecule is chiral. Yeah? This molecule over here has 2 chiral centers, but it also has an axis of symmetry, which means it's achiral. I might be top 5 smart people, no glaze. Okay, bro. Okay, just pack it up. Just pack it up. Does that make sense for everyone? Thumbs up, thumbs down, thumbs to the side, thumbs all around. So it's either chiral or achiral. C is chiral. D is achiral. And B and A are just not chiral. So the 2 structures shown represent they are either structural isomers, optical isomers, the same compound, neither isomer nor the same compound. What do you guys think? I have 2 people saying B, 1 person saying C, another person saying A or D. Well, it can't be A or D, bro. So here, the answer is A. Yeah, they're optical isomers of one another, right? It's, I mean, like they have the exact same structural. They have the same structural isomers as one another, right? But here, these ones just have a different 3D spatial arrangement to one another. So I'll keep going. Is that all good? Thumbs up, thumbs down, thumbs to the side. The last thing I'll ask: optical isomers of a medicine bind with a receptor in this. all receptors in the same way, have identical physical properties, always bind in different centers, cannot always be separated from each other. So always bind to different receptors. What do you guys think? This is a very weird way of phrasing it. So here the answer is B, yeah? They have identical physical properties, yeah? As in like the melting point, the boiling point, the viscosity are all the same, yeah? They have different 3D spatial arrangements though. Don't mix that up for physical properties, yeah? So here, it's not A, they don't all bind in the same way. It's not C, right? Always bind to different receptors from each other. They don't always bind to different receptors from each other. They could bind to the same receptor. We don't know. Like, they could, yeah? And cannot always be separated from each other. Is that true? That's absolute. We can't be certain, yeah? So here. Now we're moving on to enzymes. Does everyone understand that previous section? Because the previous section will be useful for the next section. Perfect. Okay, we have 2 people with thumbs up. What about everyone else? Any thumbs? Any two thumbs up? So we only have a couple minutes to do this one, but we'll be able to get this one through pretty quickly. So proteins have 4 structures: primary, secondary, tertiary, and quaternary. Many of you, if you do biology, you'll already know about this. The primary structure of an amino acid is made up of the covalent bonds between amino acids. Yeah? So it's made up of the covalent bonds between the literal amino acids here. So here, all these amide linkages make up the primary structure. So the primary structure is the things that hold all the amino acids together. Yeah? Does that make sense? Thumbs up, thumbs down. Thumbs to the side. Thumbs over. Come on, Swayam. You should be the first person putting a thumb up. And same with you, Daniel. Come on, guys. Gotta clutch up for the Bio Nation. In one ear, out the other. So, here we have the secondary structure. The secondary structure of a protein is made up of hydrogen bonds inside the actual amino acid. Yeah? So here, on the main chain of that amino acid, yeah, it's gonna have its amide NH bonded to another amide linkage through a hydrogen bond. Yeah? So those bonds are made through hydrogen bonds. Yeah? The same thing over here. Yeah? And they can form 2 different structures. We can either form a alpha helix or a beta pleat sheet. Yeah? Those are the 2 things we can make up. Yeah? So does that make sense for everyone? Essentially, this is the bonding from the main chain. Yeah? This is bonding from the main chain. Not the residuals on the outside. The main chain. Yeah? Does that make sense for everyone? Is that all good? So we have our primary and we have our secondary. Yeah? Primary and secondary. The primary is the covalent bonds. Secondary is only hydrogen bonds. Yeah? Then we have our, well, this is just a diagram of the beta pleat sheet. Yeah? So it basically does the exact same thing. It's just arranged in a different way. So here we have our COH, we have the NaOH, and we have the hydrogen bond between them connecting. So do you see how this doesn't include any of these residual groups? Yeah? Because that's what the tertiary structure does. So this bonds the main chain, not the residual groups, the main chain of the amino acid. Yeah? Then we have our quaternary structure. Our quaternary structure, I mean not quaternary, our tertiary structure. Our tertiary structure is the bonding between the residual groups of our amino acids. Yeah? So our amino acids, they could have hydrogen bonding. Yeah? They could have dispersion bonding. They could have ionic interactions. We'll talk about these ionic interactions in a bit. Yeah? They could have disulfide bridges. Disulfide bridges are going to be effectively covalent bonds. Yeah, they're very, very strong. Ionic interactions, they essentially, those ionic bonds, they are very, very strong. Yeah, and here we have our hydrogen bonding. There's no examples really of dipole dipole, but dipole dipole is there. Does that make sense for everyone? Thumbs up, thumbs down, thumbs to the side. Okay. So we have, dude, everyone's just loving the bio section of this, bro. Man, I'm so disappointed in you guys. Why are you guys enjoying the bio section of this more than chemistry? And then we have the quaternary structure, which is just, we have one polypeptide makes up the quaternary structure. But if we have multiple polypeptides, we have our quaternary structure here, yeah? So that's our primary, secondary, tertiary, and quaternary structure. Our quaternary structure is made up of the exact same things as our tertiary structure is. It's just between actual polypeptides, not inside the polypeptide itself. And this is what causes the bonding, yeah? This is what causes the folding in the way, if you guys do bio. This is what causes the folding, yeah? It's because of those bondings in between the molecules. Okay, I don't care about this globular. I don't know what that means. You don't need to know that. I don't even know that for med, bro. So, here, aside from the R group, the functional groups found in an amino acid are they amino groups and hydroxyl groups, amino groups and carbonyl groups, carboxyl groups, carbonyl groups and ester groups, carboxyl group and amide groups. What do you guys think? Come on, guys. Speed up. Speed. You gotta get the speed. You gotta get that speed. So BB, we have one person saying D. Here, the answer is B. Yeah? All amino acids have a amino group and a carboxyl group. Yeah? They will contain an amide group once they are polypeptides. Yeah? But they won't contain it when they are amino acids. Yeah? Here, the types of forces present in the tertiary structure of a protein are. Which ones are present in a tertiary structure of a protein? Is it A, B, C, or D? My mama kinda homeless. So we have a D, 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 D. Ah, dude, everyone's getting so enthusiastic about this. It's beautiful, isn't it? Yeah, so the answer is D here. So here we have the dispersion forces. We can obviously produce them. The ionic interactions are between those charged parts of the molecule, and we have those covalent bonds, which are the disulfide bridges. Yeah. We'll talk about the B a little bit more. And here, when referring the structures of proteins, hydrogen bonds can be found only in primary structure, alpha helix and primary structure, the primary structure and the tertiary structure, the alpha helix, the beta pleat sheet, tertiary structure, and quaternary structure. Nah, bro, that's a terrible call, bro. Don't do bio. It's so boring. You just sit there and you learn about like translation, transcription and deportation or something like that. I don't remember. Top 1 worst ideas. Bio was a high court. That's what I'm saying, bro. So here, the answer is D. So it is found in this quaternary structure. The quaternary structure contains all the bonding that a tertiary structure does. Yeah? Contains all the same bonding. So now we're talking about enzymes. Enzymes have the active site and the substrate. When they come together, they form this thing that we call the substrate. Wait, the enzyme substrate complex. Yeah. So when they come together, I finished it last year. My struggle's done. That's why it starts with a B. My bad. So here, together, they come together and they form the enzyme substrate complex. Yeah? Again, an enzyme is just a type of biological catalyst and it will decrease the activation energy required. Right? So it's just a catalyst. So, is that all good for everyone? Does that make sense? Okay. Now, we do use this lock and key model. So if they ever like, oh yeah, use the lock and key model to explain it, yeah? Essentially, what we do is that we draw the substrates joining onto the enzyme. And then afterwards, what we can show off is that here, the enzyme is left untouched. And now we have this new little molecule. Which is the thing that we want, yeah? So those, if they ever say, you can actually draw this diagram on the exam, yeah? You can draw out the lock and key model, right? They might say that as like an actual mark. They'll say, yeah, a diagram can be used to explain the lock and key model, yeah? So essentially, the substrates come together, they form the full enzyme substrate complex, and then afterwards, the enzyme is left alone with a new with that product being what we want. Yeah? Does that make sense to everyone? Does the lock and key model make sense? Yeah? There's also the induced fit model, which the Enrolo textbook doesn't talk about. And I'm going to do a little bit of research and see if we do cover the induced fit model. Because I think we might. It's out of the study design. It might be out of the study design for bio. Is it out of the study design for chem? I don't think it, because I remember being taught it for chem as well. It's out for bio. Okay. Last year. Okay. But is that all good? So we had thumbs up for that. So here, the lock and key model states an enzyme will change the shape of its active site to fit the substrate. The enzyme perfectly fits the enzyme active site. The enzyme cannot differentiate between isomers, and the enzyme can only be used once. So here, what is it? Remember, I used the phrase before, specific and complementary, yeah? What do you guys think? A, B, C, or D? We have two people saying B, another person saying B. So, he missed his bio and he's still cafe. So yeah, it is B. I'm not going to explain this one because this one's pretty self-explanatory. Again, it's specific and complementary. Yeah? So, here, enzymes have their optimal temperature that they work at. Yeah? So, enzymes, if they get too hot, they denature. Essentially, right? Remember, we have all the folding caused by the intermolecular bonds. What's going to happen is that those intermolecular bonds, remember, so I probably should have said this before. Enzymes are made out of proteins, yeah? Proteins are made out of polypeptides. So enzymes have that primary, secondary, quaternary, that primary, secondary, tertiary, and quaternary structure to them. Yeah. The enzyme then, it will like, if it's too hot, what's going to happen is that those quaternary, like the quaternary, tertiary, and secondary structures might break apart for them. Yeah. And it will just leave the primary structure. And this means it is being denatured. Essentially, we remove the folding. Remove the folding of that structure, and all we're left with is just that plain polypeptide, right? Without the folding, right? And it's basically completely useless now. Yeah. We also have, if it gets too low in temperature, it's also just going to stop working. This is simply because of the collision theory idea that we need a sufficient enough energy for a reaction to occur. Niche LARPing. I mean, some people just, I mean, I didn't even know this stuff when I was going into year 12 chemistry, right? I didn't do bio, remember, guys? Like, it's self-explanatory to you guys because you do bio, but like, I haven't, I never even looked at this. So that's why I'm explaining. Yeah? Yeah, okay, bro. So that's how denatured and low activity and how temperature affects an enzyme. If it's too high, it denatures, the bonds break between that primary, secondary, and tertiary structure. If the activity is too low, it denatures. So we've just about run out of time, and we have about 25 more slides to go through because we have to look at the Zwitter ions, the competitive enzyme inhibitors, non-competitive enzyme inhibitors. Yeah, you did start late, yeah, but I can't take up too much time. I will. Wait, not 25. Yeah, no, 25 more slides. No, 15. Sorry, 15. So I will end it here. Yeah. Essentially, this just goes through the idea of the Zwitter ions. I might just do a little recording of this last part or do another session for this last part. Yeah. Math guy can't count. Shut up, bro. I'll probably do another session to deal with these final primary, secondary, and to deal with the Zwitter ions as well as the competitive enzyme inhibitors. But going bold now, current curly hair. Okay. Okay. So, does anyone have any questions?